Yeah. So we have now discussed about the expressions, how to derive the expressions for the power and work done by water. Okay. And here we have discussed the basic thing, namely when the water strikes the plate will be moved with velocity u, and the absolute velocity is v. Okay. So now let us try to develop or understand how to draw the velocity triangles, an important concept. Okay, so for this concept is very important. Okay, so v is the absolute velocity and u is the absolute velocity of the plate. So here you can write one more thing. Okay, so the relation between these two. Okay, so this is moving with velocity v and plate is moving with velocity u, then there will be some relative velocity between water and the plate. So the relative velocity between the water and the plate, the water jet and the plate vr, okay, it's a relative velocity. Okay, is the relative velocity. Okay, so what is the relation between these three? The relative velocity, velocity of the liquid jet, velocity of the plate. So it's very basic thing. So this is the the velocity which will be the maximum. With this velocity only this plate is moving. So definitely this velocity, plate velocity, will be less than the velocity of the liquid jet. So relative velocity is nothing but v minus u. Relative velocity is, remember, this is a vector quantity. Velocity is a vector quantity which has magnitude and direction. It has magnitude and direction. So it is a vector quantity, don't forget that. Vector quantity. Okay, so vr is equal to v vector minus u vector. Okay, so with this let me proceed with the concept of the velocity triangle. Okay, so velocity triangle. How to draw the velocity triangle? Okay, so we know the relative velocity concept now. Okay, vr is equal to v minus u. So this is a vector quantity, so I am putting this. So this is a velocity triangle. It is nothing but a vector diagram. Vector diagram. Remember that it is nothing but a vector diagram. So vector diagram, okay, which means it is going to give magnitude as well as direction. It is not a simple diagram, it is drawn. Okay, so everything what we draw in the form of a triangle, it gives you a true indication of the magnitude of the different terms and the direction of the different terms we are using in the, so only it is known as velocity triangle, which is nothing but a vector diagram. So the electrical and electronics people are very much familiar with this vector diagram. They are drawing this vector diagram to show the direction of the current, phase, etc. Okay, so for mechanical engineers the velocity triangles are very limited, so we are using here, then we'll be using in kinematic of machinery, likewise we are using there and there, because wherever the velocity component involves we are using there. Okay, so one such application is in fluid mechanics we are using, and thermal engineering also we are using this velocity triangle while we discuss about the steam turbines. Okay, so all are same as I already discussed before. Okay, now let us try to understand how to draw the velocity triangle. So from this equation I can write, okay, v vector, that is the velocity of the liquid jet or water jet, is equal to u vector plus, okay, u is the velocity of the plate, moving plate, plus the relative velocity. Okay, so I can write like this. So this is nothing but one vector is here equal to one another vector plus b. So I am having three vectors. So vector v is equal to addition of other two vectors. So three vectors are involved. So I can think of the law of triangles. Okay. So in engineering mechanics also we have studied the concept of vectors. Okay, so we have applied the concept of vectors in engineering mechanics because force is vector quantity. Okay, so we will be obviously using the vector diagrams. So this triangle law, okay, using this you can have the vector triangle. So these two are in the same direction, so I can write like this. Okay, what is a triangle law? When two vectors are represented as the adjacent sides of a triangle. Okay, when two vectors are represented as the adjacent side of a triangle. Now I will take or consider these two vectors as the adjacent sides of the triangle. So now this is say u. So this is the direction in which the plate is moving, so I am taking this direction, nothing. Okay, no other concept here has been used. So in the previous slide I have shown you, previous video, there is a plate and the plate is moving this direction, so I am considering this as the direction of the plate, okay, or the surface. Now to this vector I have to add the relative velocity. So these two vectors are taken as the adjacent sides of a triangle. These are additive, which means the head of the preceding vector is placed on the tail of the subsequent vector. Okay, so this is not this is taken in order. This is taken in order. If you see the statement of a triangle, if two vectors are taken in order, which means they should not oppose, which means the head should not be placed with the head. The head will be placed with the tail of the subsequent or the next vector. Okay, so I have the blade or the plate velocity, then the relative velocity. Then if two vectors are taken at the adjacent side, the closing side of the triangle, that is this one, closing side of the triangle represents the absolute velocity. So think of the engineering mechanics. So there will be saying that if two vectors acting on a particle are taken as the adjacent sides of a triangle taken in order, then the closing side of the triangle represents the resultant force. That is what we have studied in engineering mechanics concept. Same thing we are used here. Instead of resultant force, I have the absolute velocity of the fluid jet, then I have the velocity of the surface, then the relative velocity. These are vector quantities. So this represents the directions. Also the magnitude. This much is the magnitude of u. Okay, you see here the magnitude of v is higher, so only we are able to put as v minus u. Okay, because with this only this is moving, so this will have a higher magnitude, this will have a lesser magnitude. So from this you can see this is having higher magnitude, this is having a lesser magnitude. Okay, so the difference is relative velocity. That's a so this is the taken in order. This is the law of triangle, okay, for vector addition. Okay, so this thing is very important. Okay, and you are supposed to keep in mind whenever you draw the triangle, okay, velocity triangle for any type of turbine or a pump or a compressor, whatever it may be. Okay, so this thing is very important. Now let us proceed with the basic triangle, how to develop the triangle for a turbine system. So we already know that the turbine is a device, okay, which consists of a rotor inside which there are many curved blades or curved vanes are there. Okay, and the water is going to strike the vane and the rotor is going to rotate and the rotor is coupled to the shaft, and from the shaft you are going to get the output power. All of these things we have learnt. Okay, so from that concept I will try to draw yeah, curved blade. Okay, I am drawing a curved blade. So this is a curved blade, one curved blade I am showing. Okay, and okay, the fluid is going to strike here and it's going to leave. Okay, so let me draw a tangential line to the curved blade. So tangential, which means like this. So it is tangential without any hindrance. It is smoothly touching the curved surface and leaving the curved surface like this. Okay, so this is the tangential. So what does it represent here? Okay, here it represents the relative velocity. Relative velocity. Let us assume that this is the inlet of the liquid or the water. So I'll put the relative velocity at inlet. Okay. So why I'm putting relative? Because we have two moving system. One, the liquid is moving. Okay, liquid is coming here and it is striking the blade, moving blade or the curved blade with some velocity u. Okay, so let us now put u simply. Okay, it is the blade velocity. Don't confuse much as of now. Okay, it is the blade velocity. So now this is the direction which blade is moving. Okay, you see here. So the vector relative velocity vector should be added with the blade velocity. So this is the blade direction. So I should draw the same thing here. Okay. So it is a reality. Okay, we are drawing the actual system. So this is the direction in which the blade is moving. So I should not put in the opposite direction. This is the direction which blade. So the liquid is coming, the vein is moving in this direction. So the same direction I have to follow here also. And I have to add these two as per the triangle of vector addition. Okay, these two. Then the closing side. So closing side means from here to here. Okay. The closing side represents the absolute velocity of the liquid at inlet view. So as of now I am not putting differentiating, okay, between the velocities. If you want, you can put nothing wrong. Okay, the inlet velocity, blade velocity, and here it is the blade velocity at outlet. So this is how we have to draw the three components, namely the velocity of the liquid jet, the velocity of the blade, okay, and the relative velocity. So this is as per this one, the basic thing. Okay, now let us try to expand this. Okay, let me write here what is V1. What is V1? It is the absolute velocity of water. Where? At inlet. Absolute velocity of water at inlet. Okay, what is U1? It is the blade velocity or the vein velocity. Blade velocity at inlet. Okay, what is VR1? It is nothing but the relative velocity, because both are moving. These two, water is moving, blade is moving. So you have a relative component, relative velocity at inlet. Understood? Okay. Now we shall proceed with the other terminologies. Okay, for developing the velocity triangle. Okay. So here, okay, this is where the water is directed. The fluid is directed. Okay, here you can have think of a nozzle. Okay, you can think of a nozzle here. If it is an impulse, turbine. If it is an reaction turbine, instead of nozzle, you will be having fixed blades. So already we have studied all these things, learned. Okay, already we have covered this thing. So the purpose of fixed blade is to direct. Okay, it is to guide the flow. Similarly, nozzle is also a guiding device. Apart from that, you have the other thing. It will convert the pressure energy to kinetic energy. Okay, so anyway, depending upon the position of the nozzle or the guide blade, the absolute velocity will be having its direction. Okay, then you have the direction of the blade velocity like this. Okay, now the angle made by the absolute velocity, okay, with respect to the blade direction. So this is the blade direction. Okay, horizontal I have put here. This is alpha. Okay, I repeat, the angle made by the absolute velocity with respect to the horizontal, here it is horizontal, or with respect to the blade direction is alpha. What is alpha? It is the flow angle or nozzle angle. Sorry, nozzle angle at inlet. Okay, flow, it directs the flow, so only it is known as flow angle. Or the nozzle is fixed in that direction, it is oriented in that direction, so it is known as the nozzle angle at inlet. It is alpha. Okay, similarly you have an other angle form. Let me complete this triangle. I will extend this. Okay, something like this. Similarly, the relative velocity is also making some angle with respect to the blade direction or horizontal. That angle is theta. What is theta? So you see, relative velocity is tangential to the blade. Okay, so relative velocity is going to decide, or it is going to depend upon the profile or the shape of the blade or the curvature of the blade. If the curvature is changed, automatically the direction in which the relative velocity approaches also